Okay, so this video is going to address Objective 4.3. Objective 4.3 says I can make inferences about f of x and its derivatives using their graphs. And there's different levels of this, but basically what you need to be able to do is take a look at a graph that's either f prime, or f double prime, and make inferences about the other graphs that are not shown. And so I'm going to try to show that to you here in three different scenarios. The first scenario is that you are given the graph of f of x, and I would encourage you to pause the video and take a moment to copy this graph down. It's very, very important from the get-go that whenever they give you a graph, you identify whether that graph is f prime, or f double prime. In this case, it is f, and the question is list all x values for which f has critical points. Well, critical points means the first derivative is equal to 0 or undefined. And so for us, that happens in three different places. It happens here at -3, at 0, and at 2. So we are going to say that this is true for x equals -2, 0, and x equals +2. So it happens in three different places. And then the next question is to list the local max, local min. So of course we have, actually this local is an absolute as well, both of these are, but we'll just say that that happens at x equals -2 and 2. Sorry about that. -2 and 2. And then the min happens at 0. Okay, local min. The next question is list the intervals for which or in which the derivative is positive. Well, if we're looking for a positive derivative, that means the direction of the graph, which is f, has to be going up, increasing. So a positive derivative then in this particular case would be from -infinity to -2. Now because at -2 the derivative is 0, then the derivative is not positive there. So we're not going to include it. So our interval will be -infinity to -2, not included. And then we have a positive slope again from 0 to 2, again not included. And I want to say something about this too. Sorry about that. It's going to be a little sloppy today. I want to say something about this. I'm not using brackets, and the reason I'm not using brackets is because the question is where is the derivative positive. Now I understand that is the same thing as asking where is f increasing. It's the same thing as asking for f increasing. But when they use the words increasing, it is defined with closed brackets. So if we had asked where is f increasing, it would have been along the same intervals, but we would have used brackets. Because the question is being asked where is the derivative positive, we have to take into account that at -2 and 2, the derivative is not actually positive, although it's technically increasing at that point. But since the derivative is not positive at those points, we do not include them in the solution. The next question, D, list the intervals in which the first derivative is negative. So that, of course, would be from -2 to 0, not included, and then again from 2 to infinity. Okay. E, list the intervals for which the second derivative is positive. Now, from our list, from our notes that we took in class, the little cheat sheet that we made, you can see second derivative positive. If we take it back to the original graph, that means concave up. Second derivative negative, that means concave down. So what they are really asking you to do here is to tell them where this function f of x is concave up. That's what this question means. Concave up means where f is concave up. So we're going to take a look at this graph, and it looks to me like it's concave up from -1 to 1. And concavity is defined in an open interval, so we use parentheses. And it looks to me like concave down would be from -infinity then to -1. And from 1 to infinity. Okay? So that would be concave down. Again, when the second derivative is negative, this means f concave down. So it's going to be really important for these particular problems that you understand the relationship. And it really is all listed in that little chart that we made in class. Alright, so what we're going to do now is we're going to take this example. The same graph, we're going to take it and we're going to pretend like we were never given this graph as f, but instead it was the derivative. So if I move to the next chart, you see I have here the same exact picture. But we're going to now assume that this graph is the graph of the first derivative. And that's really important. So essentially this problem has absolutely nothing to do with the previous problem. So just imagine that this is a completely different scenario. The graphs are not related to each other. This is not the first derivative of the previous graph. It's just a completely different problem. But instead of thinking of that graph as the original, we're going to think of it as the first derivative, which means you've never seen the original. You have no idea what that looks like at this point, but we do know that this is the first derivative graph. And that's important because the way you answer the questions is going to matter based on the fact that this is the first derivative. So we're going to go ahead and go with the first question. List all x values for which f of x has critical points. Well, everything is still true. If f has a critical point, then that means the first derivative would have been 0 or undefined. 0 or undefined. Sorry about that. So in the previous graph, when you were looking for critical points, you were kind of looking for these turning points where you would get a horizontal tangent line. Well, this is no longer the original. This is now the first derivative. And so what that means is we're no longer looking for these turning points. What we're looking for is where the value of our first derivative is 0. And that happens right here at -3, at 0, and at 3. So if this is the graph of the derivative, we're not looking for turning points necessarily. We're looking for when it hits the x-axis. And we do have 3 of those, but they happen at -3, at 0. Sorry, it's a little bit hard. The technology's not being very cooperative, but just trying to get through this. 3. Okay, so again, if this were the original, you would be looking for those turning points, but because it's not, because it's the derivative, then we're really looking for the places where the graph hits the x-axis, and those would be your critical points. The next question is very interesting because now it wants the x value for which f of x has relative max or relative min, local max, local min. While students always want to go directly to these turning points and think of those as the max and mins, and that would be true if this were the original, but it's not. It's the derivative. Since it's the derivative, we got to go back and think, all right, first derivative test, okay? Where do extrema happen? They happen when the first derivative changes sign, either positive to negative or negative to positive. So what you're looking for here is where does the graph change sign? Don't think of the direction. Think of the sign. So before -3, the derivative was negative. After -3, the y values of the derivative became positive all the way until 0. Then they hit 0, but they continued to be positive until 3, and then they became negative. So a lot of times the best way to address this is to make a little chart. See if this will allow me to make the chart. So I make my chart just like I would for the first derivative. And I put my CPs. Remember, our CPs are where it touches the x-axis. So I have 3 of those. -3, I have 0, and I have 3. And what I do is I look at the y values of the first derivative. And here I have negative y values, which would mean that we are decreasing. Then we have positive y values, which would mean that we are increasing. Then I continue to have positive, increasing, and then I have negative. Again, I'm not looking for direction. In this graph, I'm looking strictly at the y values. And you can see here that at -3, we've got a local min. So x equals negative 3, x equals negative 3. Let's see if I can switch the angle here. Equals negative 3 is going to be a local min, and x equals 3 is going to be my local max. And so what about 0 then? What is 0? Well, 0 is a critical point. We listed it up here, but because there's no sign change in the first derivative, we can't say that it is a min or a max. It's not neither. So we have a local max, local min. And one more time, this chart is based off of the y values because we are now looking at the first derivative, and that's really hard to kind of switch gears from when you were looking for highs and lows, but you have to remember this is no longer the original, it's the first derivative. So list the intervals where f is increasing. Well, if you make your chart, that's really easy. This function is increasing from negative 3 to 3. And because we're using the word increasing, we're going to use brackets. So we will go from negative 3 to 3. And notice I didn't exclude the 0, because if I had gone from negative 3 to 0 and used brackets, it would have been the same. If I wrote it from negative 3 to 0 and then from 0 to 3 is the same as negative 3 to 3. List the intervals where it is decreasing. Well, that would be all the ones on the outside. So negative infinity to negative 3 included, and 3 to infinity. And again, we're using brackets because increasing and decreasing is defined as including those, is defined as including the negative 3 and 3 with brackets. Next question, list where all the intervals in which f of x is concave up. Again, f of x is concave up. You are not given f of x, you're given f prime of x. So what does that mean? Well, let me scoot down a little here, set this up. What I want you to see is in class we made this chart, so let me bring it back up. It says list all the intervals where f of x is concave up. So what I normally do with this chart is f of x concave up. Here's an example where f of x is concave up. And because we are looking at the first derivative, what I do is I go from f of x concave up, I move over to the column and check out what is the first derivative doing when f of x is concave up. Well, when f of x is concave up, the first derivative is increasing. So essentially what this is asking us is, where is the first derivative increasing? Okay? Now, I looked at the first derivative because that's the graph that was given. Let me put this away. So now that I realize, all right, f of x concave up really means f prime of x increasing, then I'm just going to make a little note, f prime increasing. That's what I'm looking for. Then I'm going to go to the graph and say, hey, where is this? This is the derivative. This is f prime. Where it is increasing? Where is it going up? That happens from negative infinity all the way to negative 2. And then it's decreasing, and then it's increasing, and then it's decreasing. So I'm going to say, okay, this is negative infinity to negative 2. And because concavity is defined in open intervals, I'm not going to include the negative 2. And then again from from 0, sorry. So we have increasing all the way to negative 2, and then from 0 to 2 to 2. And concave down is going to be, so concave down is where the first derivative is decreasing. So that's going to be from negative 2 to 0. And then from 2 to infinity. Okay, so the question is, list the x values for which f of x has inflection points. Well, inflection points are where the second derivative changes sign. And if the second derivative is changing sign, then that means the first derivative must be changing from increasing to decreasing or vice versa. So what they're really asking us is, where does this f prime of x graph change directions? And that will be your inflection point. Let me use a different color. So if it's going up, and then right here at negative 2 it changes directions, that's going to be an inflection point on the original graph. So it comes down right here, another inflection point, because we're going up now. And then right here we get another inflection point. So essentially we have inflection points at x equals -2, at x equals 0, and at x equals 2. So if I were you, I would make a note. Inflection points are where the first derivative changes direction. Okay, first derivative changes direction. So let me just rewind a little bit. If this is the graph of the original function, then inflection points are the location where the graph changes concavity. Okay, so that's why we listed those two. You see concave down, up, down. But if we're looking at the first derivative, then the original, and making inferences about the original, we're not looking for when concavity changes, curvature that is, we're looking for when direction changes. So a lot of times students say, well, isn't that really just the extrema of the first derivative? Yeah, it really is. It's the turning points. Those become your inflection points. Okay, so the last thing we're going to do is we're going to take this graph and we're going to forget that it was ever the first derivative, and we are now going to treat it as a second derivative graph. Second derivative graph. So again, this has nothing to do with the first derivative at all, or with the original graph at all. It's like a completely different problem. What this means is you've never really seen the first derivative and you've never really seen the original. You've only seen the second derivative. And I can't ask you as many questions as I did about the other one, but I can ask you quite a few. So let's start with list the intervals where f of x is concave up. F of x, again, this is second derivative, and we're being asked a question about f of x. F of x concave up means, if you look at your chart, f of x concave up means that the second derivative, which is what we're looking at, is positive. So that means that I need to look for places where the second derivative is positive. Okay, so I'm going to look at the graph here, second derivative positive. That basically means above the x-axis. So that means we start at -3. This is all positive. It does hit 0, so I'm going to have to exclude that, and then it continues positive to here. So basically everything above the x-axis without including 0. Concavity is on open intervals, so I'm not going to include the 0, and I'm going to jump from 0 to 3. Having some technical difficulties, so from 0 to 3. Okay, now list where f of x is concave down. Concave down would mean that the second derivative is less than 0. So that would be all of the interval, all of the places where this particular graph is below the x-axis. And there are two places. It's -infinity to -3, and then 3 to infinity. And again, you're not looking at curvature because this is not the original graph. You're making an inference about that curvature based on the second derivative and the fact of what the second derivative being positive or negative means for the original graph. And so of course I mentioned earlier that it would be -infinity to -3, and then 3 to infinity. And of course not included because concavity is defined in an open interval. So list the x values where f of x has inflection points. Well, that's going to be any time the second derivative changes sign. So I can tell you right away, -3, before that it was negative, after positive. Now it does touch 0 here, but it continues to be positive all the way to 3 where it becomes negative. So really there's only two places where that happens. It happens at x equals -3 and at x equals 3. I could build a sign chart as well if that's helpful, like I did in the first derivative. and list all my possible inflection points. That would be anytime the second derivative is 0 or undefined. So I have -3, I have 0, and I have 3. And before this, -3 is negative, and then it becomes positive. Again, curvature doesn't matter, it's all about the y values. And then negative stays positive, sorry. Y value is positive, and then it goes to negative. So that means concave down, concave up, and concave down. So 0 is not an inflection point because we did not get concavity change. All right, list the intervals where f prime of x is increasing. F prime of x increasing. Okay, if f prime of x is increasing, what does that mean for the second derivative? Well, if f prime is increasing, and you can even check your chart, if f prime is increasing, we got the example here, then that means the second derivative is positive. And if f prime is decreasing, then that means the second derivative is negative. So essentially what's happening here is by them asking you, list the intervals where f prime is increasing, that's the same as asking you where f prime is concave up, except they're using the word increasing. And increasing automatically means you use brackets. So that's the only difference. But question D is essentially the same question as A. Our answer is going to be the same. F prime is increasing when the second derivative is positive. So, but again, because of the increasing, we got to include -3 to 0. And 0 to 3, which is the same thing as writing -3 to 3. Okay? All right, so where is f prime decreasing? That's the same as saying second derivative less than 0. So where does that happen? That's the same question as letter B. So I would say -infinity to -3 included, and 3 to infinity included. Again, we use brackets because although it's the same question as B used the word concave, which is on open intervals. So these are not brackets, these are parentheses. And then this question is using the word decreasing. So that gives you, you have to use brackets. Okay, well, this video took one graph and it gave you 3 different perspectives. So I'm hoping that this will help you complete your worksheet today. If not, email me, text me, or whatever you need to do to get the support you need to complete your assignment. Thank you.